Welcome to the second day of our workshop. And the first speaker of our morning session today is Professor Ralf Schiffler from the University of Connecticut. And he's going to talk to us about knot theory and cluster algebras. So please go ahead, Ralf.
Thank you very much. Thank you, Rak-Kyeong, for the invitation, and I'm happy to speak here. I will report on relatively recent progress on the connection between knot theory and cluster algebras. This is joint work with Véronique Bazier-Matt, who is postdoc here at Connecticut. I have a picture of her. Coincidentally, this picture was taken this morning when she was giving a talk on the same subject in the Paris Algebra seminar. Well, for you, it's already February 15, I guess, but here it's still February 14. So I will start with an overview. So I want to connect knots to cluster algebras. So let me give you a knot. Okay, this is the figure 8 knot. And well, this is a diagram of the figure 8 knot. Well, I'll use the letter K for a knot diagram. It could also be a link. It doesn't really matter as long as it is. If you want a link, then you should pick an orientation of every component. I will consider this knot diagram as pretty much as a simplicial complex. So I will use the notation K0 for the crossing points. And K1 for the segments. And maybe here I should be precise what I mean by this. So I will label the segments on the knot. Start here, 1, and then I just follow the knot, 2, 3, 4, 5, 6, 7, 8. So a label is really between two crossing points. I'm often, sorry, a segment is between two crossing points. So often people in topology would consider what I labeled 1 and 2 as a single segment, but for me these are two different segments. And then we'll have regions, which I denote by K2. And then you can convince yourself that the number of segments is twice the number of crossing points. Number of regions is the number of crossing points plus 2. And to this picture, I want to associate a quiver. And yeah, quiver is the same as an oriented graph. And let me do this here in the example. Well, let me tell you first the notation. So Q0 are the vertices, and they're in bijection with K1. So the segments of the knot give you the vertices. And let me draw the segments, the vertices of the quiver here in the same way they appear there in the left picture. Okay, and then we need arrows. So the arrows, let me just say they go clockwise around the crossing points. So what do I mean by this? There's a crossing point here in the knot made up by the segments 1, 6, 2, 7. And I'm saying I want to draw arrows which go clockwise around it. So I want to have an arrow from 1 to 6, and then 6 to 2, 2 to 7, 7 to 1. And I do this for all the crossing points. So the second crossing point will give me an arrow from 6 to 3, 3 to 5, 5 to 2, and 2 to 6. And there's 2 more, 1, 4, or 8, 8 to 3, 3 to 1. And finally 4 to 7, 5, 5 to 8, and 8 to 4. Okay, so this is how you draw the arrows. And then, well, you see every crossing point gives you an oriented 4 cycle. This crossing point here corresponds to the 4 cycle here. It's clockwise, this cycle is oriented clockwise. Also, every region gives you an oriented cycle. This region here, 147, gives you an oriented cycle in the quiver which goes counterclockwise. And then we do the usual thing, you do clockwise regions minus counterclockwise regions, that gives you a potential. Yeah, let me write this as maybe clockwise cycles or the K0 cycles. So those that correspond to crossing points, and then subtract the K2 cycles. These come from the from the regions. So potential. Okay, so very good. And when we have the curve with a potential, then we can associate an algebra, the Jacobian algebra. So denote by B. It's the Jacobian algebra. This algebra is a quotient of the path algebra of the quiver by the two-sided ideal determined by the potential. So it's generated by the cyclic derivatives of the potential. And so that's B, and they also have something called A, that's the cluster algebra of the quiver. And well, if you're familiar with cluster algebras, you might object now because the quiver has 2 cycles. But it is not hard to get rid of these 2 cycles. So you can find an equivalent potential, remove the 2 cycles, and take that quiver instead. Okay, and then these 2 objects, they talk to each other. There's categorification. Or, well, depends which way you want to go. You might want to call it decategorification. Yeah. And so our goal, well, we have the connection here. Our goal is to make this connection meaningful. So what we want to do is construct cluster variables. Well, these are generators for the cluster algebra. Generators. to be clear, we don't want all generators. There will be infinitely many generators. We just want a few of them, special ones, which carry information about the knot. And our approach, well, there's two approaches. Our approach is to construct B modules. Which we'll think of as representations of the quiver. And use categorification. And this is what I'm going to talk about today. And a different approach would be to construct a mutation sequence. Directly in the cluster algebra that produces the cluster variables that we're interested in. So this is the first approach, is what I'm going to talk about. This is today. And the second is our work in progress. Okay, so this is what this talk is going to be about. Any questions up to here?
So can you go in the opposite direction and starting from the quiver with potential build a sensible knot? Or?
Well, if it came from a knot, then yes. But I mean, not every quiver will give you a knot. There's very strong restrictions on the quiver. Every vertex has 4 arrows, for example. Yeah. But if you know it comes from a knot, then you know the clockwise arrows will correspond to the crossing points. The arrows themselves to segments. So it's kind of drawing a dual graph.
Okay, thank you.
Maybe I could remark here an important observation is that the quiver doesn't see whether your crossing is an overcrossing or an undercrossing. Right, I didn't use that information here in the knot. I see I know the segment here from this line goes above the line given by 7,6, but the quiver doesn't see that information. This information is of course crucial for the knot. If I move the overcrossing into an undercrossing, then maybe the knot becomes trivial completely, but the quiver would be the same. So the quiver doesn't see this difference. So to recover this difference, we'll see later how we still can distinguish this difference. Okay. Okay, so I said we want to construct a B module, so we want to construct quiver representations, and we'll do we do this for every segment. We define actually an indecomposable B module as follows. We give it a name called TI. So the first step is to construct a partition of the set of all segments, K1, into subsets KIT. So this partition will depend on the chosen segment I. How does this go? So KI0 is going to be the set of segments. Well, first I take I, and I take all the segments that CI. And I want to illustrate this right away in the example. Okay, so let's take I equal to 1. And so I want to take the segment 1, and then I want to take all the segments that see the segment 1. So in other words, the segments that bound region together with 1. So you have this 4 and 7, and then you have the outside region, so 6 and 3 as well. So here the K10 would be the set of red segments 1, 4, 7, 6, 3. Then we want to do KI1, and well, it is almost the boundary of K minus KI0, but only almost. So there's something else you have to do, which this is a little bit technical. I don't want to go into this here now. And well, and if I had defined what that means, then the other ones are, you just continue in the same way recursively. It's K, there will be KI2, KI3, and so on, but I should point out here that this is a finite union. In our example, this is a small example, so the only other set here would be KI1. If you take away all the red segments and then look what you have is there's take the boundary of that, you get all the edges that are left over, 2, 5, and 8. Okay, let me move this again a little bit. And so we want to construct a representation of the quiver. Remember, the segments are of the knot are the vertices of the quiver, and these sets determine the dimension at every vertex. So the dimension of our representation Ti is equal to D at every vertex and K. Right. So I'm switching always back and forth between calling the segments vertices or segments. There we have a decomposition, a partition of all the segments or a partition of the vertices of the quiver. And yeah, so here in this example, all the red vertices are not present in the, well, the dimension is 0 in the representation, and the only non-zero vertices are 2, 5, and 8. yeah, so, and that each of these, the dimension is 1, so let me write k is a field. At each of these vertices, and I have to define the arrows as well, so maybe I go back and look what the arrows look like. The subquiver I'm concerned with is the one given by 2, 5, and 8, and you see there 5 is the source of the 2 arrows that you have there. So the subquiver looks like this. And so here I will have to define maps on these arrows. Okay, so this is the point 2. I don't have time to write this also. Again, this is, yeah, there's a couple of cases here to consider. You need to accept the fact that if you have an arrow in the quiver, an arrow alpha from x to y, you need to define a linear map on this arrow for defining the representation ti. And the fact you need to accept here is that the difference of the dimensions at these 2 vector spaces is at most 1. This comes from the construction of the partition. And then there's 2 easy cases. If one of the 2 vector spaces is bigger than the other, then you have these 2 matrices. So you have the identity with a 0 row at the bottom or the identity with a 0 column on the left. And if the dimension is the same, then there are 2 possibilities. Either you have the identity or you have a Jordan block with eigenvalue 0. And so we have all these cycles in the quiver. If you follow an oriented cycle, if you go around the 4 arrows around a crossing point, for example, and compose all these 4 maps, you will always get the Jordan block. The definition is made like that. The same is true if you go around a region. If you go around the cycle of a region, then the composition of the maps in the representation will also be the Jordan block. Okay, so yes, to illustrate this here and to show the difference here, the dependence on the segment, on the chosen segment, I have here an example where we choose the segment 2. And again, in red, you can see here the K20, all the segments that see the segment 2. And then K21 has 4 segments left, 1, 3, 4, and 8. And the subquiver, see, these are all vertices, all segments that attach to a single crossing point, and therefore the subquiver here is an oriented 4 cycle. And here this definition, the last part of the definition comes into play. The 3 of the arrows are the identity, and the other one is, the last one here is the Jordan block.
Ralf, I have a very quick question. In the first example you had, when you choose the segment, and then you say the other segments that see that segment, sometimes I'm in the first example, you when you go up here, so you choose 3 and 6 and 7 that see segment 1, but why does 2 and 8 not see 1?
Oh, so by seeing it, I mean, there is a region, and if you stand in that region, then you see the segments that are red. So there are 2 regions that are adjacent to 1. They're incident to 1, right? The outer region and this region, and you take the boundary of these 2 regions.
I see. Okay, fully understood.
Can I ask a question also?
Yeah, sure.
Are you going to tell us when you use a Jordan block and when you use the identity?
I would prefer not to. It's a little bit involved. It depends on these and more that I haven't specified here.
Okay.
I could talk about this afterwards. We would need a bigger example there. Yeah. It has to do with the fact that here you see you have, well, that's not the real definition, but so this, I should use a different color maybe. This crossing point, I wanted it different. For this crossing point, all four segments are of the same dimension. And which means that one of the arrows at this crossing point must have the Jordan block. That's one thing. The other thing is in this region, every segment is of the same dimension, which means that one of the two arrows in this region must have the Jordan block. Yeah, so that's why the arrow from 4 to 8 is the one which has the Jordan block. This is a necessary condition, but not sufficient. Okay, part 2, I said we want some information about the knot, so let me talk a little bit about knot invariance. Well, and actually the only one I want to talk about is the Alexander polynomial, which was introduced by Alexander in 1923, and it is denoted by delta. It's a polynomial in t to the plus minus 1/2, and it's defined up to a power of t. In our running example, this polynomial is 1 minus 3t plus t squared. Yeah, this is a very old knot invariant, has been heavily studied. This has interesting properties. Let me just mention a few. It's palindromic. So the sequence of coefficients is a palindromic sequence. If you evaluate the Alexander polynomial at 1, you get plus or minus 1 if you have a knot, and you get 0 if you have the link with at least 2 components. And there's several approaches to the polynomial, several ways to construct it. Geometric, algebraic, or combinatorial. The approach we are using here is the approach of Kaufman via Kaufman states. Kaufman did this in 1983. So first, we have to choose two adjacent regions. Let's call them R1 and R2. Well, this is the same as choosing the segment, since the regions are adjacent. So this looks like this. This is segment I, and then one region is R1, the other one is R2. And then now what is the Kaufman state? We choose adjacent pairs. these pairs consist of a point, a crossing point, and a region. So the region has to be adjacent to the crossing point. This is a case in K0 times K2. We do this such that every point and every region except R1, R2 appear in exactly one pair. Okay, so for example, if I use again I equal to 1, so I don't want the two regions that are adjacent to 1. But use these pairs, for example. So I will put a dot for the pair. So this dot here means I have the region. This dot means I use this region and the crossing point. So in other words, these pairs correspond exactly to the arrows in the theorem. Okay. This choice of pairs is called the Kaufman state. And the Kaufman states form a posets. Kaufman states form a poset, a lattice actually, with cover relations given by transpositions along segments. Okay, so how does this go? You have from segment J, and I have my Kaufman state, which has markers for this segment. And then in another state, it's like if I have this situation that I have two markers on the segment J, I can move them. This is called a transposition. And you see there's a direction you can do this counterclockwise around the points, for example. And this direction determines an order on the poset. This is the covering relation. And then if you can go from one state to another by a sequence of these moves, then the first is smaller than the other. And Kaufman's theorem says that there exists a weight function from the set of states to Z, well, the ring for the Alexander polynomial, such that the Alexander polynomial is the sum of all these states, the weighted sum of all these states. Well, there's also a sign involved here. So each state comes with a plus or minus sign, and then there's the weight of the state. Okay, so I should have, here's a picture. Yeah, so here's a poset for the figure 8 knot on the left. You have 5 different Kaufman states. So I start here. Let's start at the bottom. I have in this picture I have my 4 markers. This is still for the segment 1. The segment 1 is this one here. So there's no markers in the 2 regions next to that segment. This is, so here we have a first state, and then you can see I can change the configuration by doing the transposition along this segment, which was labeled by 2. And I would get the 2 markers change position like this. Or I can make the same transposition at the segment labeled 8 here and move the markers across. And once I have done these, I have the options of, well, the opposite options. If I did 8, I can do 2 afterwards. If I did 2, I can do 8 afterwards. And then finally, this one's maybe a little harder to see. Here I can use this transposition at 5 to go 1 step higher. And so if you think about the module that we have defined, which I have symbolically illustrated here as 5, 8, 2, in this notation, you see what the submodules are. You can easily construct the submodule lattice of this module. And you see that these 2 lattices are isomorphic, and the submodule, the dimension of the submodules are exactly given by the operations that you had to do to come to the state. So here you had to do operation 2, operation 8, and the dimension of the submodule is, well, it's 1 at vertex 2 and at vertex 8. Okay. Last 3 minutes, I want to tell you about results. So let's go right for the theorem. So for all segments, first of all, the state coset is isomorphic to the coset of submodules. The F polynomial, which is a gadget from cluster algebras. So you can think of it as being the cluster variable. F polynomial of Ti. Well, actually, I can write the definition here. F Ti is the sum of all submodules then you have the F polynomial is a polynomial in Y1 through Y. As many as you have vertices in Q, so J in Q0, Yj, and you raise it to the power dimension of Lj. So this is called the F polynomial. The F polynomial specializes to the Alexander polynomial. Okay, under which specialization you have to set Yj equal to negative t. If the segment J goes from an undercrossing to an overcrossing, negative t inverse in the opposite situation, and the segment J goes from an overcrossing to an undercrossing, and -1 if neither of the 2 cases happens. So if you have J either stays below or stays above. So this is what I said in the beginning, the quiver and the module do not see whether you have an overcrossing or an undercrossing. This only is recovered here at this last step when you do the specialization from the F polynomial. So maybe we have time for writing down this example. So the F of T1, I already wrote the modules here. You have to sum over all the submodules. So the polynomial will be 1 plus y2 plus y8 plus y2 y8 plus y2 y5 y8. And then, since this is an alternating knot, the specialization will send the even indexed variables to negative t and the odd indices to negative t inverse. So the specialization will give you 1 minus t plus t square, and then there's one which is negative here, so it will be another minus t again, which is the Alexander polynomial of the grade. Okay, so I'm out of time, so let me leave you here with the image. If you would use the segment 2 instead, you see you get a quite different poset structure, but you still get the same result for the specialization. Thank you very much.
Thank you very much for the very interesting talk. Are there any questions in the audience?